Okay, let's talk about some properties of continuity. If b is a real number and f and g are continuous at x equals c, then the following functions are also continuous at c. So if you multiply a constant times a function, then that new function is going to be continuous at c. The sum of two functions that are continuous are going to be continuous, and so is the difference. So the difference of two functions will be continuous. Even the product of two functions that are continuous are going to be continuous, and so would be the quotient. As long as the denominator is not 0, the quotient would also be continuous. So all of these functions are continuous within their domain, which means they have no breaks. So polynomial functions are all continuous within their domains. Rational functions are all continuous within their domain. Now the key is within their domain. Radical functions are continuous within their domains, and trig functions are continuous within their domains. Well, putting all that together, since x squared is a continuous function within its domain, and so is cosine x, then the product of x squared cosine x would be a continuous function. Since x is a continuous function and tangent x is continuous within its domain, then x plus tangent x would be continuous within their domain. And since x is continuous and sine x is continuous, then x over sine x would be continuous within its domain. So you can test for continuity and determine x plus tangent x. This function is undefined at pi over 2 plus k pi, where k is an integer. And the reason is because tangent x is sine over cosine x. So these values would not be in the domain. So this function would not be continuous at those points. This function, sine of 1 over x, remember this is the one that oscillates, goes up and down. Okay, but we're not going to let it equal 0. We're going to say it equals this if it doesn't equal 0, and then we're going to say, well, it's going to equal 0 otherwise. Well, first of all, 1 over x is continuous everywhere except 0. And the sine function is continuous for all real numbers. So it follows that the sine of 1 over x is continuous everywhere but x equals 0. And so therefore the limit does not exist as x approaches 0. So since the limit does not exist, then this function is discontinuous at x equals 0. Now this function is identical to the previous problem, except that the limit as x approaches 0 does exist. So you can use the squeeze theorem and show that this limit right here is actually 0. So the limit is 0 and the functional value is 0. So therefore this this function is continuous at x equals 0. See, over here, the reason this one wasn't continuous at x equals 0 because the limit of this function did not exist, so therefore the limit as x approaches 0 did not equal the functional value at 0, which was 0. But over here, if you can show that this equals 0, if you can show that the limit of this function is 0 as x approaches 0, then therefore the limit equals the functional value, so it must be continuous for all numbers, all real numbers. Now, discontinuity falls into two categories. You have removable and non-removable discontinuity. A discontinuity at C is removable when f can be made continuous by redefining f of c. So let's see how we can remove the discontinuity. Well, this function is defined to be this rational function if x does not equal 5, and it's defined to be 6 if x equal 5. We ran into this one earlier, so you probably already know the answer here. The only point of concern is at x equal 5, because that's the only place that this is undefined. But if you take the limit of this function as x approaches 5, you're actually going to get 10. But the functional value is defined to be 6. So what you could do is you could change this value here from 6 to 10, and then when you make that change, then now you have the limit of the function is equal to 10, and also the functional value is equal to 10 as x equals 5. So therefore we remove the discontinuity at x equals 5. Okay, this one is discontinuous at x equals 2. You can see that if you plug 2 in, you're going to get 0 in the denominator. But you're also going to get 0 in the numerator. So let's see if we can factor the top and bottom. I'll factor the top as difference of squares and the bottom as difference of cubes. And when I factor that, I get 2 minus x over 2 minus x here, which is 1. So that's just 2 plus x over 4 plus 2x plus x squared. Well, now if you evaluate this as x approaches 2, then you get 2 plus 2, which is 4, and then 4 plus 4 plus 4, which is 12. So the limit of that function as x approaches 2 is 4 over 12, or 1/3. So in order to remove the discontinuity, you would have to reassign this so that f of 2 equals 1/3. Because if f of 2 equals 1/3, then the functional value at 2 is 1/3, and the limit would be 1/3. So that would remove the point of discontinuity. We're going to finish this section with the intermediate value theorem. Basically, the intermediate value theorem says if f is continuous on a closed interval from a to b, and f of a doesn't equal f of b, and k is any number between f of a and f of b, then there's at least one number c in the interval such that f of c equals k. And so let me show you that. Okay, so here's a continuous function, and it goes from x equal a to x equal b. Okay, and notice that f of a and f of b are at different heights, so they're not the same, and that's what the theorem says. F of a must not equal f of b. And let's say k is any number, so let's say k is right here. So it's a number between f of a and f of b. So in other words, a is at this level, right? And b is at this level. Let me move that down a little bit so just to make sure that it's between them. Okay. All right. So here's the k, and it's definitely between f of a and f of b. Well, then there must be some number c in between a and b such that f of c equals k. So this point right here would be the point c, and then f of c would have to equal that k value. Okay, so the mean value theorem tells us that. Now let me tell you where that's helpful. Where that's helpful is, let's say f of a is a negative number, and let's say f of b is a positive number. Well, if f of a is a negative number and f of b is a positive number, then there must be a number k in between those two numbers that is 0. So there must be a 0, so it must cross the x-axis somewhere in here. So therefore, we can prove that there's a root, that somewhere between a and b, there's some root that makes this function 0. Okay, so let me show you this, an application of the intermediate value theorem. It says, okay, prove that this function has a 0 on the interval from 0 to 1. Well, we know the function is continuous from 0 to 1, so that takes care of that. And notice if you evaluate the function at 0, you get a negative number. And if you evaluate it at the other endpoint, you get a positive number. Well, since f of 0 is negative and f of 1 is positive, we can conclude there's at least one value c within the interval from 0 to 1 such that f of c equals 0. And there's a tricky little algorithm you can use to find that. It's actually pretty simple, but it can be it can require computation, quite a few computations to get it close. But let me show you. Let's take this same function. Okay, so we know from up there that there's a number between 0 and 1 that will give us a 0, that will make this function 0. Okay, so I don't know what it is, so I'm just going to shoot for the number in the middle. So the number between 0 and 1, so just add 0 and 1 together and divide by 2, and that gives me 0.5. Okay, well, now let's see if 0.5, what it gives me. If I plug 0.5 into this function, you get 0.5 cubed minus 2 times 0.5 minus 1. I got a positive number. I got 0.125. Well, remember, this gives me 0.5 gives me a positive y value, but 0 gives me a negative y value, so there must be a root between 0 and 0.125. So let's see, is that right? I'm sorry, not 0.125, between 0 and 0.5. Because 0 gave me a negative, 0.5 gave me a positive, so there must be a root between 0 and 0.5. So let's find the point halfway between there. So that's going to be 0.25. Now when I evaluate the function at 0.25, I got a negative number. Well, so f of 0.25 is negative. Okay, but remember f of 0.5 was positive. So now I've trapped the solution between 0.5 and 0.25. So let's find the halfway point between those two numbers. Well, that's 0.375. So now let's evaluate the function at 0.375. I didn't write the number down, but when I plugged in 0.375, I got a negative number. So 0.375 is negative. And the last positive one was at 0.5, so the solution now is trapped between 0.375 and 0.5. So then you can find the midpoint of those two numbers by adding them together, divide by 2, and you get 0.4375. And if you do this long enough, you can get as close to the answer as you want. Okay, now here I'm just assuming there's only one root, so that could be an issue if there's more than one root in that interval, but there's only one root in the interval from 0 to 1 for this function. So this would work if we just kept doing this and took it out farther and farther. And the farther we take this method out, the closer we'll get to the actual root. Okay, that's pretty much it on this section on continuity and one-sided limits. And I've got one more section on Chapter 1 I'm going to talk about, and then we're done with Chapter 1.